Okie dokie. So we're talking about waves, and I'm going to show you two types of waves. First, so imagine that this is a slinky, okay, and you are holding the slinky. Somebody's holding the other end. So you're holding the slinky and you are moving it back and forth like this, and it goes one, 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 one like that, and a wave moves down that way towards your physics buddy at the end, who is also holding the end. Okay, so that's one type of wave. And we could do the same thing where you are holding the end of the slinky and your physics buddy is down here holding the end of the slinky. And what you do is you grab a section of the slinky and you pull it in and then you release it. And so you can imagine the slinky's kind of going do 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 do, or something like that. So we have this region of it's sort of expanded and then compressed and then expanded and compressed and expanded. And these are both waves and they're both moving in this direction, but it's important to look at a section of the slinky and see in which way it's actually moving. So in the top example, let's say we put a piece of tape on the slinky right here and we watch it as the wave goes by. So as the wave goes by, that section of the slinky is going to move down and then it's going to move back up. This section of the slinky does not move along the slinky down to your physics buddy's hand. And then similarly, if we were to take a look at this region, choose a different color like purple, okay, if we were to look at this region of the slinky, let's say we put a piece of tape on it or whatever, as the wave moves down the slinky, this little region doesn't go down the slinky. It just sort of vibrates back and forth. So it would go like this. So these are two different types of waves, even though they're both waves in a slinky, and you're creating the wave, and the wave's going down to your friend. This we call transverse. So you might want to write this definition. It's transverse because the direction of the wave is perpendicular to the direction of the medium. So write that down. The direction of the wave is perpendicular to the direction of the medium. Whereas with a longitudinal wave, the direction of the wave is parallel to the direction of the medium. Okay, so that's important. Definition of a wave. And so you might be thinking, oh, I know what waves are. Surf's up, dude. Yeah, that was me. But, well, so sure, ocean waves, that's one example. But, in physics land, we're going to be more specific. And we're going to say a definition of a wave is, it is a disturbance in a medium. And we'll talk about what all these terms mean. Disturbance in a medium that transports energy but not matter. So, a disturbance in a medium. So if we talk about, let's pretend we have an ocean wave here. So here's our ocean wave. It's not breaking yet. Here's our ocean wave. A disturbance in a medium. So the medium is whatever material the wave is actually passing through. So in this case, the ocean, or the water molecules, would be the medium. A disturbance, meaning they're not perfectly still, they're moving around. And the wave itself transports energy but not matter. So if we were considering a little water molecule right here, okay, and here's the shore over here, and so the waves, let's say, are going in this direction. In some ways it's counterintuitive, but this water molecule does not move in towards shore. This water molecule just sort of goes up and down like this, and it's the energy within the wave itself that goes this direction. So just like with our slinky example here, this part of the slinky doesn't move down the slinky to your friend. It just moves back and forth like this. And the same thing happens with water molecules. So we're going to talk about ocean waves, and we'll talk about sound waves, and there are actually a lot of really interesting things related to this. So that's not going to erase. We're going to get some white marker here so we can do some erasing like that. Okay, so let's talk about the parts of a wave. We're going to get pretty specific here. So we got a definition, but let's take a look at our ocean wave and start labeling stuff that we know. So here's our ocean wave, and you can imagine what this is. And this is the water level if no waves were passing by, right? If it were perfectly calm, the surfers would be bored, but there'd be no waves, and so we call this equilibrium position. So that's equilibrium position, and if you've been doing graphs of sine and cosine functions, which you've probably seen at this point, you know, this is the x-axis or whatever. So this is our equilibrium position. This could be a string, or pressure in air waves, or sort of the water level in water waves, which is probably easiest to think about. The height of the wave, so from equilibrium to the crest, there's an R in there, hey, there we go. So that's the crest. So from equilibrium to the crest is the amplitude. Let's label that guy. Amplitude, and then here the bottom part, this is called the trough. I always think I'm misspelling this when I spell it. Who knows, maybe I am. So the distance from the equilibrium to the trough, that's the amplitude. Alright, amplitude. And then there's this word called wavelength, which if you've been studying sine and cosine graphs, right, and we're thinking about this as time, the time for one complete wave, we call the period of oscillation. When we're looking at them in terms of distance, the distance for one complete wave, or the length of one complete wave, you guessed it, we call wavelength. So our variable is lambda, and that is wavelength. So the wavelength, again, is the length of one complete wave. So middle crest, middle trough to middle, or from the crest to the crest, or from the trough to the trough. Each of those is the same distance, and we call that wavelength. All right. So I'll put this in here. We could talk about also the period of oscillation. So period of oscillation, this is the time for one complete wave. And that would be measured in seconds. And then the reciprocal of that we call the frequency. So frequency, that's the number of waves per second. So frequency is waves per second, and a formula related to period and frequency. Period is 1 over frequency, therefore frequency is 1 over the period. Okay, and waves per second, or cycles per second, is sometimes referred to as hertz. So in physics we'll see that unit. Units for frequency are hertz, units for period of oscillation are seconds, and then wavelength, this is the distance, so we'd probably be using meters. Same for amplitude. Alright, and then we have so if we think about, this is the distance of one wave, right? And velocity, distance per time. So we have this formula here where the wave speed or velocity, and that's going to be equal to frequency times wavelength. So this is like how many waves per second, and this is how how long each wave is, and if we multiplied them, we would end up with velocity in meters per second. Okay, so that sounds good. What's this? You guessed it. Those are people doing the wave. And so if we consider, and I have a video to show you of that, if we consider, so the medium, right, a wave, let's say the wave is going this way, right, around the stadium. So that's the direction of travel of the wave. The medium, the thing that's actually moving, would be the people's hands. And maybe they're standing up, so it's their whole body, okay? And if we think about the direction in which that is traveling, right? So the medium, this person's arms go, this poor person, here they are on YouTube. So the medium goes up and down, whereas the wave itself goes this way. So notice how these are perpendicular. So we would call this a transverse wave. And every time I see this done, I think, oh, if we were all physics people, we would want a longitudinal wave as well. So we would move our arms to the side. This is this person's arms, and our arms would go like this. So it'd be a longitudinal wave as well, but that never happens. Oh well, maybe in the next life. So let's see what else we have. That's pretty cool. So transverse wave, sporting event. And then we can talk about the speed of waves. So we also, in physics, talk about waves on a string very frequently. This is something we can do in class. So we'll have, maybe we're holding this, or both ends are attached. So a guitar string would look like this. You wouldn't actually see the wave this distinctly. But here's a wave traveling down a string. This happens. And if we talk about the wave speed, so if we talk about how fast the waves go, it's going to be related to the tension in string. And so if you're a music person, maybe you play guitar or banjo or whatever, and you're tuning the guitar, what you're doing is you're actually increasing or decreasing the tension. And you can picture it, in your mind, it goes dung, 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 as you increase the tension. So when the tension increases, the speed increases. And then this down here, this is called the mass density. Mass density, meaning the heavier the string, the slower it's going to move. So I have tried desperately to try to learn piano. I think it's fascinating, but I just have no talent. Anyway, I'm not bitter. So here, these are this is an image of piano strings, and so some of them are so heavy that they're actually wrapped, or piano wire we would call it. They're actually wrapped, and so we see the ones over here. These would be the dun 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 dun, right? Really heavy strings, and so slow-moving waves, and we would hear them as a low frequency. We'll get to that. And then over here, these would be higher. And if we look at, so here's a grand piano. This would be really cool. But over towards the right, we have the ding, 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 really high frequency, and so the strings are short and they're light. And then for the boom, 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 the long, low frequency, we have really long strings, and so they produce this low frequency. And you can even see they're wrapped. Those look heavy. Oh yeah. All right, so the speed of the wave in a string depends on that stuff. We're going to pause and then talk about sound waves in part 2.